mission to avert cosmic disaster is underway. Its success depends on a bold gamble against long odds. The goal? Discover what lies within the comets that orbit our solar system at deadly speeds. The challenge? Send a spacecraft 80 million miles and punch a window straight to the comet's heart.
First man on the moon, Lewis and Clark coming out west, Magellan going around the coast. We're doing something that nobody has done, and we're going to be the first to really go and find out what comets are made of.
Encountering a comet's just fantastic. Everything about it is exciting. It's 23,000 miles per hour. That's when the impactor is going to get smashed by the comet. It vaporizes.
Engineers have done an incredible job of designing and making sure this thing works. But I think we'll still need some luck.
We have only one chance. It's all or nothing on the first try. You're moving much too fast to stop and get back in front of the comet again.
The question is, are we going to make it through alive? A piece of dust the size of a pea could literally destroy us.
The mission is hit or miss.
Roger, I got you 5 by 5.
And everyone on Earth has a stake in the outcome. This impact is harmless. To do damage, you need size and speed. A galactic impact can be fatal.
Almost every planet in the solar system has one giant impact where if it had been a little bit bigger, it probably would have destroyed it. Oh my gosh. When you see this, you realize the power, just the enormous power. Something that was quite small came in so fast, just takes your breath away.
50,000 years ago, an asteroid fragment heavier than the Empire State Building penetrated the Earth's atmosphere over what today is northern Arizona. It struck with the force of 1,000 Hiroshima bombs and left a crater almost a mile across. Yet this is a pinprick compared to the damage that awaits us. Comets move up to 3 times faster than asteroids. More speed, more impact. A comet is a catastrophe looking for a target. In 1994, it found one.
You know, the rumors spread around that a comet was going to hit Jupiter, and since you haven't a clue what's going to happen, really, every astronomer in the world went out there to their telescope and looked.
On July 16th, 1994, astronomers watched Shoemaker-Levy 9 as it sped towards Jupiter's dense atmosphere. We used to think a comet hurtled through space as one solid piece. Gravity was tearing this one apart. The comet split into 20 huge chunks. Some larger than the island of Manhattan. What followed were the largest explosions ever witnessed in the solar system. For Earthlings, it was a cosmic wake-up call.
If you saw the images of Jupiter taken afterward, you see these spots. And those spots were comparable in size to the area of the Earth. Very big. And you could imagine that Earth was not isolated in the universe, that it's not perfectly safe. bad things happen.
The first rule of war is know your enemy. But if a comet is Earth's mortal foe, we're in the dark. No one really knows what's inside a comet. Then, astronomer Mike Belton had a big idea. Exploit a comet's great speed to pierce its mysterious heart.
We need to go into space and to the comet itself in order to see what's underneath the surface by colliding something with the comet to create an enormous explosion or liberation of energy that excavates this enormous hole.
Call it a cosmic biopsy. It sounds good, but could it work? No one ever collided a man-made object with a comet.
He came to me in my office and said, if I ran a 500-kilogram spacecraft into a comet at 10 kilometers a second, how big a hole would it make? And I did some simple calculations, and we came up with the answer that it might blow a hole 300 to 500 feet in diameter and probably 50 to 100 feet deep. At that, Mike said, aha, we have a mission.
In 1999, NASA greenlights a mission called Deep Impact. The goal, blast a hole in a comet and discover what's under the surface.
We've been hit by comets. We've been hit by asteroids. This time we get to take the revenge, and we're going to slam into the comet itself.
NASA's first step, assemble a dream team of experts to get the project off the ground.
1,000 PSI.
Astronomers, astrophysicists, celestial navigators.
Into the sequence, but we got to get that schedule laid out. I think fundamentally we agree.
The mission sounds like Mission Impossible. The scientists envision a spacecraft that will leave the Earth, travel across deep space on solar power, constantly relay information back to Earth, intercept a comet going 66,000 miles an hour, shoot another craft called an impactor into the comet's path, create a giant crater, record the impact, and send the data back to Earth. No one said it would be easy.
Even though you gave it the lockup times for high-rate telemetry over the high-gain antenna, the lockup rates on the 10 bits per second low-gain antenna are very long.
We've had flybys of comets before, of course. Those missions were difficult, but nothing compared to the Deep Impact mission where you're actually trying to hit it. It's sort of like trying to pick off a bug in mid-flight with a bullet shot.
Program managers John Marriott and Monty Henderson are charged with turning the scientists' drawing board into a working spacecraft.
What happens is you sit down with the different scientists and they will explain what their ideas are. And they seem so foreign, so difficult, near impossible. You leave the meetings kind of scratching your head going, oh, okay, what can I do about this?
In November 1999, engineers at Ball Aerospace begin scratching their heads to work out the details.
So let me get this straight. If I rotate the spacecraft like this, we're going to release the impactor spacecraft to head towards the nucleus of the comet. We're going to do a divert burn to miss the nucleus with the flyby spacecraft so that the flyby spacecraft doesn't impact the nucleus.
Keeping the comet in the field of view.
And then we're going to image the crater and do all this, turn to a safe mode, and then go through the coma, the tail of the comet, into the dust field and survive.
And all we have to do is make it light enough to get it off the ground.
Well, that's enough challenges to keep us busy for a while.
On this program, nobody can be afraid to take a risk because they're not relying on any historical program to say, oh, this is how they did it in the past, because no one's done this before.
Blasting a comet is a whole new Big Bang theory. The next hurdle, testing the theory right here on Earth. NASA has trained its sights on the ultimate moving target, a comet. But which one? At any moment, hundreds of comets are speeding through our solar system, but only a handful will be in range when it's time to shoot. The Deep Impact team targets a 9-mile-long comet known as Tempel 1. At the outset, this is their best view of the target. Charting a course for the spacecraft that will intercept the comet falls to celestial navigator Don Yeomans.
Yeah, the spacecraft is going to fly about 250 million miles to the comet, and it's our job to tell them where the comet is when they arrive to within about 20 miles.
Comet Tempel 1 approaches Earth every 5 years near the orbit of Mars. That is Deep Impact's destination. If the mission succeeds, it will shed light on a mystery to rival the dark side of the moon.
Humankind has been fascinated by comets for thousands of years because nobody knew what they were, and although the mystery is somewhat different than it was then, there are still mysteries because the comets are so hard to study.
Astronomer Michael Ahern has spent his career trying to fathom comets. It's like studying a riddle wrapped in a fog.
By the time the comet gets in close to the Earth, it is surrounded by this coma. They're enveloped in this dust and gas that would extend from the Earth to the Moon. We don't know what is inside the nucleus. We only see the material that is stripped away from the surface.
One way to study comets is to analyze the trail of particles they leave in our atmosphere. NASA scientist Mike Zolensky sends high-flying jets to trawl for comet dust falling to Earth. But the dust comes from the comet's surface, not its core.
As comets circle the sun, the outer material gets processed. And we want to know what's really going on with the material that's deep. And Deep Impact's main goal is to expose that material to the surface so we can look at it for the first time and see what's the interior of a comet like. Is it a giant honeycomb mass? Is it a solid snowball? Is it rocky? Nobody knows.
The heart of a comet is like a fossil, from a time when our solar system was just gas and dust. 4.5 billion years ago, that dust and gas began to congeal, forming the inner planets. Other dust was flung into the cold corners of the solar system. Slowly, it coalesced. In the process, water, carbon, methane, perhaps complex organics combined and became comets. They number in the trillions. Soon, one of them will have a close encounter with a spacecraft, if the Deep Impact team can pull it off. Since the team has just one shot at the comet, Peter Schultz wants a preview of the crater the impactor would make. To see what might happen, he has devised a way to make a miniature comet and blow it up. He'll use a big gun and some freeze-dried witchcraft.
Ah, man, that's cold. We really don't know what comets are made out of. What we do know is that it's complex organics, and so we need to stew up something interesting. A little bit of coloring because there's organics in this material. And then we add some sugar. And then we add some nitrogen, not too much, just a dash. And then finally, the piece de resistance. This is my secret mix for a comet. It's Worcestershire sauce. In fact, one possibility for a comet is that we'll have this mixture of carbon and hydrogen and nitrogen, oxygen, all put together in a stable position when it's really cold. But when the impact hits, we may get an explosion we didn't count on.
When the spacecraft reaches the comet and releases the impactor, it will likely produce one of three results. If the comet's interior is hard, an explosion, but a small crater. If the comet is extremely soft, the impactor could be swallowed up and disappear without a trace. But if the comet is as dense as NASA hopes, the collision will produce a crater big enough to reveal what lies beneath. To simulate the impact, this huge gun will fire a bullet at astronomical speed.
Showtime, you guys almost ready? Okay. Yeah.
For this test,
The film's in.
the core of the homemade comet is soft and porous. Atop, Schultz's hard crust.
What we're going to do is to slam through this target at a velocity or speed of 4 miles per second. This upper surface has no chance. It's going to be broken apart, pulverized, as the projectile goes down into the target and rips the surface apart. At least that's what we think we'll see. .62, that's good. Okay, I'm ready then. Okay. Got the dolphin. Oh!
It happens in a flash.
Jeez, that really blew a hole.
Already, Schultz sees something odd.
That's a surprise. I didn't expect it to be, number one, that big. Number two, well, it shows a sharp edge. The interesting thing is it shows this sharp edge. But I gotta see this. I gotta see this in real time. I just gotta go see it.
The hypersonic impact was recorded by a 500 frame per second camera.
Oh, there it comes. That's amazing. The whole thing begins to crack apart. It splits. And we're having an explosion below the ground. And this impact went in, buried itself, and now it's just poof.
Is this a preview of what will happen when impactor and comet collide? No one knows.
Here I'm playing in the sandbox, and now we're going to do the real thing at velocities we can't even do, with masses we really can't do, and we'll watch this real time. It's like the culmination of the grandest experiment that you can really think of.
For now, this test is pie in the sky. First, NASA has to get a spacecraft off the drawing board.
How about, in the interest of brainstorming, you just check out some wild ideas?
After decades of space travel, you'd think building a spacecraft wouldn't be rocket science.
One side, instruments on the other.
But it is.
That looks like it'll create a problem during separation.
Could be challenging if we didn't have this balance perfectly.
Especially when you're building a spacecraft that will rendezvous with a comet. The first constraint is size. The craft must fit atop a Delta II rocket, a position that requires the craft to balance within 1.3 millimeters.
Hey, let's not forget, we only have 2,400 pounds to work with. That's all that the launch vehicle can lift.
Engineers will use a renewable source of fuel for the journey. Large solar panels, But getting them to fit has them stumped.
Problem is, we don't have enough power. That solar array has to be bigger, and we've taken up the fairing envelope.
If we go back to our baseline concept of the single solar panel here, that would get us the solar array area that we need.
But a single panel upsets the balance.
Yes, remember, we're trying to maintain symmetry for solar pressure.
Okay, so we want to keep everything centered about the...
Yes.
Then we have bifold door option, where the panels then fold outward.
The thing there is you won't get any power until those arrays deploy. What if we take the same general spacecraft and we turn it sideways like this? And that way we can just have two solar array panels like this.
The new configuration gives them the power they need and gets rid of one hinge. One less thing to go wrong.
Every little piece of the spacecraft gets that level of detail and that type of consideration. So it's hundreds of trades that you go through before you come up with what you ultimately send off into space.
All those trade-offs produce a design with these key components: an impactor, 2 telescopes, an oversized solar array, and an antenna to receive signals and beam information back to Earth. Two years from drawing board to scale model.
Critical design review is over, and we went from paper to model.
In January 2002, the next stage begins.
Now all we got to do is build the real thing.
To assemble the spacecraft, the engineers need a garage as big as a football field. And every inch must be kept spotless. A speck of dust could disrupt the electronics. A skin flake could obscure the optics. A single human hair could sabotage the entire mission. More than 100,000 parts will go into this spacecraft. And with no room for error, each is checked and rechecked, down to the torque on every bolt.
There are a million ways that you can screw up, and we've probably thought of 999,000 of them.
Year to year. For the cable to come out. Okay. You got it. That's perfect.
As components are built, they're rigorously tested. Frozen to reproduce the temperatures of space. Shaken to simulate a launch.
Okay.
The system is designed to expose engineering flaws before they jeopardize the mission. 6 months into a 3-year assembly, they find one. The telescope's main mirror is cracked.
During testing, we had one of the mounts on the primary mirror on the HRI, the high-resolution telescope, crack on us. And that's where we're worried about that might go again.
The telescope's mirrors can't budge. A deviation beyond 1,000th of an inch might as well be a mile.
If we have this type of failure in the mission, then we lose all of our science on our primary high-resolution imager. So we absolutely have to get this resolved, or else we don't fly the mission.
If they solve the problem, they'll launch the most powerful telescope ever sent into deep space and get a close-up view of the impact from hundreds of miles away. Another problem looms: shielding their brainchild from a hostile world. Comet debris moves 30 times faster than a bullet. To survive out here, you'd better be prepared to take a hit. To replicate conditions in space, engineers head for Denver, home of one of the fastest guns in the West. The bullets fired from this barrel simulate comet debris, traveling at lethal speeds.
A grain of sand moving at 10 kilometers per second, it doesn't seem like much. but it's got a lot of explosive energy, as much as a hand grenade.
This mock hand grenade will be fired at 15,000 miles per hour.
So what are we going to run this at?
950 psi.
16,000 psi.
The target? An unorthodox space shield designed by engineer Joel Williamson. A single heavy shield won't work, so Williamson tries layers of thin, lightweight plates.
What we're hoping is that these layers of copper will stop the particle as it expands through these layers and stop it from hitting that vital equipment that's on the interior here of the spacecraft. So are you ready to load?
Sure.
Okay.
Everyone evacuate the building. We're going to unshunt the firing line and evacuate.
The shot will hit its target within a millisecond, so everything is recorded by high-speed cameras.
5, 4, 3, 2, 1, 0. Push firing button, ensure the red light goes out.
Looks good.
Okay.
Instant replay confirms a direct hit.
If that rear wall is doing its job, the debris cloud will be stopped, and the material that's on the inside will be protected. If it's not doing its job, it'll rip right through the rear shield, and we'll lose everything that's on the interior.
The moment of truth.
All right. Now looks like we got some piston damage here. Got a big hole in the front and no hole in the back.
Looks good.
What I'm seeing here is that the particle went in the area here. We expanded. Look at how large some of these craters got, larger and larger and larger as we went through each of these layers. And then finally, when we got to the end, it stopped it. Then this is going to take it right on the chin, and it's going to keep right on going. Won't even blink if it gets a particle this size. It's bigger than what we thought we could handle.
Confident words spoken on Earth. But will the shield stand up to the harsher test of space? May 2004. 8 months from launch of a suicide mission into outer space. This is the nearly complete mothership that will carry an impactor to a comet, record the collision, and send real-time images back to Earth. The impactor itself has a simpler mission. Hit the comet and make a crater. The bigger, the better. Mechanical engineer Alice Finney leads the impactor design team. Her first challenge is basic. What should the impactor be made of?
Our favorite material is really aluminum or graphite composite. They are the strongest and the lightest things you can use. That was the absolute material that the scientists didn't want us to use. They wanted us to use copper. No one has ever built a spacecraft out of copper.
The advantage? When it hits the comet, the impactor will vaporize, and copper won't be confused with elements spewing from the comet's core.
Yeah, we're still messing with we're trying to decide how big this is going to be.
Right.
Next problem, what shape will all this copper take?
So let's see if I can take the impactor out here. You see
Once again, goals collide.
the camera that's guiding
The scientists want a sphere for maximum impact. The engineers need a platform for their instruments. Finney's team tries dozens of shapes and reaches dozens of dead ends. Finally, a design emerges. The business end of the impactor will be a layered copper hemisphere. Weighing 800 pounds, it packs a punch equal to 4.5 tons of TNT.
The impactor is designed to operate for 24 hours and then get vaporized. So It's not like I can have the sense of love for it like it's my baby. I mean, the whole mission is to go and be obliterated. So I'm okay with that. That's what it was going in.
The odds are stacked against it.
In fact, if you were, say, like a fighter pilot on the Deep Impact spacecraft, and you had to ram this comet, your human reactions probably couldn't do it. You are flying 100 times faster than a rifle bullet. The comet goes from being a point that you could barely resolve with your eye into filling the screen in a matter of seconds, and you just couldn't hit it yourself.
Software straight out of Star Wars will help the impactor locate and hit the comet. But the task is harder still. It can't strike the comet just anywhere. The point of impact must be illuminated by the sun, so we can see it. Here's how it should work. First, the impactor is released. It locates the comet on its star charts. 2 hours before impact, its camera isolates areas of light and dark. It's programmed to avoid bright spots near the edge and dark spots anywhere.
We have only one chance. It's all or nothing on the first try. At 10 kilometers per second, you're moving much too fast to stop and get back in front of the comet again.
With 9 minutes to go, and the comet 5,000 miles away, the impactor makes a final course correction. Then it waits, directly in the comet's path. At Ball Aerospace, program manager John Marriott sweats the details. Thousands of them.
I worry about not just that the comet's coming closer, not just that I have to launch at a certain date. I worry about, is the comet tumbling? Is it rotating faster or slower than we've expected it to do? I mean, there are so many unknowns. I never want to fly a failure.
Success hinges on getting the mothership into the right position. But the gyroscopes that will guide it have suddenly developed a glitch.
John, we got some more information on the welds. I want you to take a look at it.
Okay.
Hairline cracks have been discovered on a set of gyroscopes identical to those on the Deep Impact spacecraft.
This one has the good weld depth on it, and this is the weld depths that we have on ours.
A catastrophic crack of the weld is of great concern for us. We've got to make sure we analyzed it and really understand what the ramifications are, risks to the program. So we need to bring in some other experts to help us out with this one.
Spacecraft orient themselves through a foolproof method of celestial navigation. Optical star trackers compare the craft's position with the known stars, so it always knows exactly where it is. Gyros keep both mothership and impactor stabilized and control their motion in 3 dimensions. The least flaw in any of the gyros, and the craft may be flying blind.
We've got to see the impact of the impactor into the comet to 1/3600th of a degree accuracy with our telescopes. So the pointing requirement in that direction is incredibly precise. The pointing requirement back to the ground for telemetering the data back, over 80 million miles, is within 1/4 of a degree.
If it's not catastrophic, what is it?
This is
Just a minor problem.
The problem is, if to get to these gyros, I got to completely disassemble the entire box.
John Marriott breaks the dreaded news. Their $350 million spacecraft may be sabotaged by faulty welds in the gyros.
Complicate matters even further, we don't have a very good process other than destructive testing to verify if the welds are in fact good.
With the launch imminent, it's too late to repair the gyros, much less replace them.
What's good enough to launch these things?
The mantra that we have is the Comet won't wait. That's kind of the driving force behind everything we do, is we've got to make sure we're not doing anything that could delay the launch of this mission. That's an absolute launch window that we cannot miss.
All through the night, a crisis team wrestles with the gyro problem.
Is that if I were cruising through space right now and we didn't have gyros, you guys would figure out a way to hit this comet. In this business, the folks are so creative that there's somebody out there that will figure this out. They'll never be 100%. But I'm willing to bet on the creativity of the people. If you were up there and something happened, what would you do?
To soften vibrations during launch, they devise an ingenious mounting platform. But they won't know if it works till the ship's launched and on its way. Six months until launch of the Deep Impact mission, and engineers begin the most critical stage of assembly, joining the impactor to the flyby with the precision of a Swiss watchmaker.
Just tighten it, lightly torque them, and then the critical moves over.
Engineer Lorna Hess-Fry must ensure a smooth fit and a smooth release.
First spacecraft I've taken from cradle to grave, we say, and so my team's success is resting a lot on this, because if we don't separate, we don't hit the comet.
Armed with a detailed checklist, Joe Gallenbach mans the last line of defense against failure.
If something's wrong and we don't catch it, it doesn't get caught. And God forbid we do miss something and it goes up and we have a disaster.
Space missions have been derailed by something as simple as a crane dropping its precious cargo. The whole mission literally hangs by a hook.
Obviously, if anybody sees anything that we're missing, say stop. Anybody in this room can say stop. Let's do it. Okay. Everything okay over here? Let me take a peek up top. It looks good right now? Plenty of room?
We're verifying right now all of the clearances are pristine. When the impactor is released, we don't want any sort of friction to conk it off. So this mating interface has to be exactly right.
With precision the goal, the impactor descends by centimeters.
Okay, is everybody ready? Coming down. What are you on your front one? 100. What's this one? 75.
A perfect fit.
We're good right there, guys. All right.
A milestone passed. 5 years of engineering comes to an end. They've built a heroic spacecraft for a Superman mission, overtaking an object moving faster than a speeding bullet and more powerful than a locomotive. Its fate now rests with the launch team.
Take PSC purge press open. Open. And
Launch morning, January 12th, 2005. For the first time, program managers John Marriott and Monty Henderson have nothing much to do but cross their fingers.
This is the amazing time. I mean, it's hard to describe. You just stand here and you just admire.
It's been an incredible effort. There's been a lot of personal sacrifice on the count of essentially the whole team to get us to where we're literally sitting on top of the rocket ready to go today. It's an unbelievable feeling.
Every NASA mission has a narrow launch window. Deep Impact's window is razor thin, just 1 second to fire the rocket.
We have done a recent analysis in the hurricane loads that says we can tolerate loads.
The weather's good, but not ideal.
And, only have non-detrimental structural impacts.
Mission control management are looking at what might be a problem with upper-level winds. That would, of course, be a problem for this rocket, but otherwise they say that the weather looks pretty good.
As the impact creates a crater, we'll watch debris that gets flown up, and we'll get a chance to look inside the comet.
Estimated sizes of meteorite impact craters and came up with the answer that it looks like this.
And verified PSD purge pressure is 400 plus or minus 25. Verified.
About 1 rocket in 20 ends in failure.
Looking for your readiness to proceed with the count.
Nitrogen regulator lock-up pressure.
2 minutes to ignition. 2 minutes to do or die.
To leave Earth at the exact second, on the exact launch attitude out, to encounter 80 million miles away a comet. The precision and the calculations there have been incredible. We have instantaneous launch windows. We can't delay. We either go on that second or we don't go.
T-minus 15. 10. Wrong. 7, 6, 5, 4, 3, 2, 1. We have ignition. Liftoff of a Delta II rocket carrying Deep Impact, NASA's journey to unlock the mystery of the solar system's origin.
Roger that, I did. Great news.
Up on T plus 36 seconds, we are now supersonic.
It's just seconds after launch of an historic mission to a comet. Deep Impact's flight engineers take control of the spacecraft. They're waiting for a signal it's detached from the rocket, and all systems are go. But a crucial first step, the tumbling spacecraft has to stabilize, then, within minutes, deploy its solar panels and point to the sun. All this, or the mission is lost in space.
T-minus 2 minutes, we go to internal power, and the battery will keep us powered for 45, 48 minutes long. We certainly don't want the battery to expire before we're pointed with the solar rays on the sun.
A strong, locked signal from the spacecraft means the solar panels have deployed.
I don't have any.
The signal they pick up is weak.
I dropped that again.
Out again.
Ominously, the signal swims in and out.
When you go out of lock, the spacecraft antennas could be not pointing correctly. It could be a sign that your attitude isn't stable.
If the spacecraft is unstable, the gyroscopes could be to blame. Their welds may have cracked, and the team's worst fears come true. Barely 7 minutes remain on the battery. A countdown to heartbreak.
The spacecraft is now on its way to a 6-month mission to impact the comet. Comet does not have its assessment.
58 minutes elapsed since launch.
We could go 65 minutes without having direct solar ray power.
How much time has elapsed?
58. 58 minutes elapsed since launch.
Symbol lock.
You got symbol lock?
Then, a steady signal.
In lock. Got it.
The panels have deployed. Deep Impact is on its way to meet a comet out near the orbit of Mars.